Hello, I am Alejandro Gómez Yepes from the University of Vigo and I'm going to present this paper. Multi-phase machines present numerous benefits in comparison with three-phase ones, including inherent fault tolerance and reduced current rating for given total power. High DC link utilization is very attractive for AC drives because it provides several potential benefits. On the one hand, the high DC link utilization permits reducing the DC link voltage for a given machine, and this in turn makes it easier to comply with voltage limitations imposed, for example, by standards or by other equipment of the system, such as batteries. It also alleviates the need to connect several switches in series, and it reduces the magnitude of the dead time harmonics, for example. On the other hand, high DC link utilization allows increasing the AC side voltage for given DC link voltage, and this makes it possible to extend the speed range or to reduce the current and hence the losses. A conventional method to attain high DC link utilization is to use square voltage waveforms, but this implies extra current harmonics. It has been proposed in the past to use XY passive filters with high impedance in the XY plane, which is not related to electromechanical conversion, but even with these filters there are still harmonics in the alpha-beta plane, which causes undesired torque ripple. An alternative method has been recently proposed for 5-phase drives, which combines XY filters with a PWM method that injects suitable XY harmonics. This permits to achieve at the same time a high DC link utilization, low XY current thanks to the attenuation of the filter, and no torque ripple because the PWM method does not inject any alpha-beta harmonics. Such PWM method was very simple because it didn't have trigonometric functions, it didn't have to solve optimization problems, and it didn't need to distinguish between different overmodulation in regions depending, for example, on the modulation index. Conversely to, for example, most of the existing PWM methods for high DC link utilization. However, such method was only suitable for 5-phase drives with symmetrical winding, not for other phase numbers or for asymmetrical windings, which are also very common. In view of this gap in the state of the art, this paper extends such PWM strategy from 5 phases to any number of phases with either symmetrical or asymmetrical windings. In this manner, high DC link utilization is obtained with simple PWM and without torque ripple, and assuming that a suitable XY filter is used, the current distortion is negligible. For symmetrical windings, the spatial displacement between any two consecutive states or phases is 2 pi over n, for example 2 pi over 6 for 6 phases. For asymmetrical windings, there are several winding sets of 3 phases each, which are spatially displaced by pi over n electrical radians, like in this figure for 6 phases. Nevertheless, machines with symmetrical windings and a phase number that is multiple of 3 can also be understood as several winding sets of 3 phases, but with a displacement of 2 pi over n instead of pi over n. In order to achieve a simple PWM method, it is very useful to divide the fundamental period of the phase voltages into several regions that are symmetrical with respect to each other. For this purpose, it is useful to sort the phase voltages from the lowest to the largest at each instant, as we do here with a 9-phase machine with symmetrical windings, where we only saw half a cycle for simplicity. In this manner, for symmetrical windings, we have a total number of 2n symmetry regions of length delta equal to pi over n each. For example, for 9 phases, we have 18 symmetry regions of 20 degrees. And this symmetry will be exploited to obtain a simple PWM method. Now we will try to do the same for asymmetrical windings instead of symmetrical. For asymmetrical windings, we also sort the phase voltages from lowest to largest at each instant, but in this case they will be for n symmetry regions per fundamental period instead of 2n, and each of these regions will have a length of pi over 2n. This means that for asymmetrical windings we have twice as many symmetry regions as for symmetrical windings. Furthermore, although for symmetrical windings all the regions were symmetrical with respect to each other, for asymmetrical windings we have n over 3 basic patterns, so that some regions are symmetrical with respect to A, some other with respect to B, etc. This can be observed here for a 6-phase machine with asymmetrical windings, although here we're not showing explicitly the sorting of the phase voltages for simplicity. And although for symmetrical windings it was enough to just consider a vertical symmetry axis, for asymmetrical ones, some cases, which we denote with an overbar, we will also have to consider a horizontal symmetry axis. For instance, for the 6-phase machine with asymmetrical windings, the region B with overbar is symmetrical with respect to B by using a horizontal symmetry axis, and this also means that they are equivalent to each other if we reverse the order of the voltages after they are sorted from lowest to largest. And in this slide we show the resulting symmetry regions not only for 6 phases with asymmetrical windings where we have 2 basic patterns, but also for 9 phases with 3 basic patterns, for 12 phases where we have 4 basic patterns, and for 15 phases with 5 basic patterns. For asymmetrical windings, it will be necessary to identify the symmetry region where the phase voltages are at each instant without using trigonometric functions. So for this purpose, we will define several variables. Vk is the element number k in the array of voltages sorted from lowest to largest. Eta k is the index of Vk in the array of phase voltages Va, Vb, etc. Gamma is equal to the k value such that the absolute value of Vk is the minimum of the absolute values of the phase voltages. Finally, we have these variables defined in this manner depending on these two conditions where m goes from 1 to the floor function of n over 6. For example, for a 6-phase machine with asymmetrical windings, let us focus for instance on this region A. First, we sort the voltages from lowest to largest in this region. According to the definition of gamma, we can see that in this case gamma is equal to 4 because V4 is the voltage with the lowest absolute value in that region. In addition, eta 4 is 3 because V4 is the same as Vc, which in turn is the third element in the array of the phase voltages. It is also straightforward to obtain that eta 3 is 6 and eta 5 is 1. And substituting these two values in these formulas for m equal to 1, we finally obtain these two values for these parameters. If we perform analogous computations for asymmetrical windings with phase numbers of 6, 9, 12 and 15, we can see in these tables that for each of the regions, the parameters eta, gamma, plus minus m give unique numerical combinations for each of the regions, and hence we can use these parameters to identify the region at each moment. The only exception is for C and C over bar with n equal to 9, because then for these two regions the numbers are the same for the parameters 1 and 1, but we have checked that with the method this is not relevant and it works nevertheless even in this case. This figure depicts the general view of the proposed carrier-based PWM method, where V are the original alpha-beta modulating signals, which are also the control output. V and T are the components injected to maximize the DC link utilization in the subspaces other than alpha-beta, which are not related to electromechanical conversion, assuming that the windings are sinusoidally distributed. And V' are the final modulating signals to be compared with the carrier to generate the firing signals for the inverter. The proposed PWM consists of two main parts, an offline procedure and an online procedure. In the offline part, we generate and store some matrices that are required in this block. For the case of symmetrical windings, we only need a single matrix C, whereas for asymmetrical windings, we need to compute n over 3 matrices CR, one for each region R. And during the online execution, we use such matrices C or CR to compute V and T and V' for the modulation. Now we tackle how to generate V and T from V during the online execution for symmetrical windings. So basically we just sort the phase voltages from lowest to largest, then we multiply them by the matrix C, and finally we rearrange them using the same indices that we obtained from the first sorting. On the other hand, for asymmetrical windings, we also sort the phase voltages from lowest to largest. We compute these parameters that we have previously defined in order to identify the region R in each sampling period, and depending on R, we select the respective matrix CR and we multiply it by the input sorted voltages. And finally, we rearrange them using the initial indices in order to obtain the no torque voltages. Regarding the offline procedure, to obtain these matrices, we have to solve a linear system of n equations and n unknowns, where the unknowns are the no torque voltages, and this should be done only once for the case of symmetrical windings, but for asymmetrical windings we have to do it for each of the basic patterns for the regions. Namely, first we have two equations that impose that the projections of the no torque voltages onto the alpha and beta axis are 0 in order not to disturb the torque. All the other equations are obtained by solving the optimization problem that the DC link utilization should be maximum. This one means that the lowest and largest values at each instance should be equal to each other in absolute value. These expressions impose that the lower gamma minus 1 voltages are all equal to each other. These other equations impose that the other n minus gamma elements should also be equal to each other. Although for the particular case of even number of phases and symmetrical windings, this equation should be replaced by this other one. For instance, for 6 phases with asymmetrical windings, this is the resulting matrix for region A, and we can see that many of the values are identical to each other, which also simplifies the implementation and execution of the method. Furthermore, the matrix CB for region B is exactly the same by just interchanging these two elements. In this figure, we compare the improvement in DC-link utilization provided by several switching methods in comparison with the conventional PWM method without any zero sequence, which would correspond with the horizontal line of zero improvement. Solid lines correspond to symmetrical windings and dashed lines to asymmetrical windings. Yellow denotes the conventional PWM method with a single zero sequence injection, which is also known as min-max method. Black denotes the conventional PWM method with multiple zero sequences, one per each 3-phase winding set, assuming the neutral points are isolated. Blue is square wave voltage, and red is the proposed carrier-based PWM with XY harmonics injection. It can be seen in this figure that the proposed PWM in red permits achieving almost as high DC-link utilization as a square wave, especially as the phase number increases, but without the torque ripple associated to square wave. The enhancement provided with respect to conventional PWM with zero sequence is substantial in most cases, but especially when the number of phases is odd and not a multiple of 3. The only case where there is no improvement is for 6 phases with symmetrical winding, where they are exactly equivalent. The simulation results are performed with a 6-phase induction motor with asymmetrical windings. The choice of asymmetrical windings is especially interesting because the previous method was only suitable for 5 phases with symmetrical windings. This machine has 1 pole pair, these electrical parameters, and the rated current is 2.4 amps. The inductances of the XY filter in the alpha, beta, and XY planes are these ones, in accordance with previous publications. This filter is here considered for all the switching methods. The low torque is 6.2 Nm, the fundamental frequency 50 Hz, with switching frequency of 10 kHz, dead time of 3 microseconds, and all these results are performed in MATLAB Simulink. This figure shows the phase voltage references for each of the switching methods. All of them have the same fundamental voltage, which is the one in green, and we can see that the proposed PWM in red has a voltage peak that is almost as low as for the square wave in blue, but substantially lower than the conventional PWM with zero sequence in black. These plots are the stator current waveforms for each of the switching methods. All of them have some distortion, even the conventional one because of the dead time, although obviously for a square wave and for the proposed one there is some more distortion, although it is greatly attenuated by the XY filter. This is the complex spectrum of the current vectors in the alpha, beta, and XY planes for the different switching methods. It can be observed that both the square wave and proposed PWM have some harmonics in the XY plane in order to maximize the DC-link utilization, but their magnitude is moderate thanks to the attenuation of the XY filter. On the other hand, in the alpha-beta plane, the harmonics of the proposed PWM are as low as for the conventional PWM, whereas the harmonics of the square wave are very large in this plane, leading to torque ripple. Such a statement is corroborated when we show the waveforms of the torque ripple, where we can see that it is much larger for a square wave in blue than for the other methods in red and black. So in this table we compare the main figures of merit of the simulation results, where we can see that square wave and the proposed PWM have larger current harmonics than the conventional PWM, but the harmonic losses are almost negligible with respect to the fundamental one, thanks to the attenuation provided by the XY filter. In addition, the proposal manages to avoid the torque ripple of the square wave and having a torque ripple similar to the conventional one, but the DC-link utilization is increased very much with respect to conventional, and it's almost as high as for a square wave, but without its torque ripple. To sum up, we can conclude that in this paper, starting from a simple carrier-based PWM method that was originally proposed only for 5 phases asymmetrical windings, we have extended it to any phase number n with either symmetrical or asymmetrical windings. The symmetry of the phase voltages during the different regions within a fundamental period has been exploited for the sake of simplicity, even for asymmetrical windings. The proposed PWM method attains nearly as high DC-link utilization as a square wave, but without the alpha-beta harmonics and torque ripple of the latter. The enhancement in DC-link utilization in comparison with the conventional carrier-based PWM with zero sequence is significant in all the cases except for 6 phases with symmetrical windings. The current harmonics in the XY plane can be disregarded provided a suitable XY filter is adopted. Simulation results obtained for 6 phases and asymmetrical windings validate the theoretical outcomes. Some possible subjects of future work include, for example, providing further details about the implementation, the harmonic content, the filter design, the computational burden, performing experimental results, etc. This is all. Thank you for your attention.